Right, welcome back, grade 12s. We're going to now look at the reactions of the alcohols up here. Again, like normal, I'll jump to the PowerPoint first and then come back to the notes. So what I've done here on the PowerPoint is I've got a summary of the reactions. Button doesn't want to work for a second, don't know why. From current slide. I've got a summary of all the reactions of the alcohols on this page here. You can have a look, so you can see that there's a number of different reactions that take place. You get substitutions, eliminations, and obviously combustion. All the organic compounds will burn pretty much the same way that they did for the others. Specific types, you get halogenation, dehydration, and esterification. Those are the three different types. We'll see how these form their products in a minute, and then we'll go through some examples. There's a nice summary slide for you to use when you're studying. Maybe you can improve it a bit, and then you should be able to write this out from memory if you know this stuff properly. Okay, so we'll go through them one by one. Here we look at the first one. It's a substitution reaction, halogenation. So if it's substitution, means something must go on and something must come off. If it's halogenation, that means a halogen must probably go on because there wasn't a halogen there originally, and something's going to come off, probably the OH. And in that case, you're going to form a haloalkane. Here's an example, and there's the reaction conditions. Now, let me talk you through the specifics first. So there's an example of a simple, the simplest, methanol. And methanol can react and form a haloalkane if you react it with HBr. Okay, so hydrogen bromide will react quite nicely with methanol. And what's going to happen is the bromine is going to go on. The bromine is going to go on, and the water and the hydrogen from the HBr are going to combine to make water. Sorry, the OH and the hydrogen from HBr are going to combine to make water. The hydroxy group, hydroxyl group. Now, with primary primary alcohols, the hydrogen bromide can just react straight away. That's what it means here. Primary and secondary alcohols, you need the concentrated sulfuric acid and the sodium bromide to produce the hydrogen bromide. It won't just react with hydrogen bromide. You need these two to react to make the hydrogen bromide. The hydrogen peroxide, it'll be a slightly higher temperature as well, and that will produce the HBr, and then it's the HBr that reacts with the alcohol, producing your haloalkane, in this case bromomethane, and your water. Now, for tertiary alcohols, you don't need these extreme conditions. You don't need the hydrogen bromide to be made in the reaction by reacting sulfuric acid with sodium bromide. Obviously, remember, this is just an example. Sodium bromide, you could be using sodium chloride here, any halogen it'll work with. But here, it'll just react with the hydrogen bromide itself. So you don't need to actually produce the hydrogen bromide in the reaction. Here, tertiary alcohol like this one. So this is going to be 2-methyl propane 2-ol. And that's going to react with the HBr, and it's going to make 2-methyl 2-bromo, well actually 2-bromo 2-methyl propanol. You always say these groups in alphabetical order. Plus, of course, your water. So there's your 2-bromo 2-methyl propane, 2-methyl 2-bromo propane, and there's your 2-methyl propan 2-ol. So when you look up the reaction conditions here, you need to find a way to write them out. I wrote them out better on the previous slide. Primary and secondary alcohols, you need this concentrated sulfuric acid plus the sodium bromide to make the HBr. But the tertiary will just react with room temperature, and they'll just react with the HBr itself. Okay, so that is the first reaction of the alcohol that we're going to look at. Second reaction is an elimination. So something's going to come off, and you can bet your bottom dollar it's going to be the OH and probably another hydrogen. And so you're going to lose water. It's going to be a dehydration. And what you're going to form is an alkene. Okay, if you lose a thing off each of these carbons, they're going to have to make another bond. And so what you get in this case is the OH comes off, and one of the hydrogens off this carbon comes off, and you get a double bond formed, and so you get your alkene. and then obviously with the H and the OH you've gone and made water. Now here's a primary and here's a secondary. Okay. Now in this case it doesn't matter which one of these hydrogens comes off, it's going to make no difference to the final product. The product's going to be this one. But here you've got possibilities, because if this OH comes off, a hydrogen could come from here, or a hydrogen could come from here to make the water. Alright? And now if the hydrogen comes from here, you're going to get a double bond here. If the hydrogen comes from this carbon, you're going to get a double bond here. Now, how do you know? Well, there's a little rule. It's kind of the reverse of the rule we saw before in the alkene reactions, where when you were adding onto that double bond, the hydrogen always went onto the carbon where there was the most hydrogens. Now it's the reverse. The hydrogen is lost or removed from the carbon that's got the least hydrogens. Okay, kind of the same rule, just in reverse. So in this case, when you've got a choice between taking a hydrogen from here and making the double bond there, or taking the hydrogen from here and making the double bond here, obviously it doesn't matter if it's this one or that one, because compounds can spin on the single bonds. The hydrogen is going to be removed, and this carbon's only got 2 hydrogens and this one's got 3. So your double bond will be formed here, one of these hydrogens will be lost, and this is going to be your major product. What I mean by major product is you also get a minor product. You get a small amount of the other one formed, and that is because of the intermediate in the reaction. Now you don't need to know about that, but there's a more stable intermediate formed in this case when hydrogen is lost from there than when the hydrogen is lost from the end. You don't need to know that, you just need to know this one is the major product, and then you also need to know what would be the minor product with the double bond here. Okay, with double bond formed there. So obviously if we're going to name this, this is going to be butene. Alright, and this was butanol. Okay, so that's the reaction of that's the elimination reaction, and the one before we had the elimination was the substitution reaction, where the bromine went off and the OH came off. Here you're just losing. You're losing the OH and you're losing the hydrogen. So that was elimination. Right, here's another substitution reaction. Now we're going to look at this reaction in a lot more detail when we do esters. So here we're going to do it fairly briefly. You make an ester when you react the alcohol with a carboxylic acid. And you make an ester and water. Now when I do the esterification with the carboxylic acids, I'll go into a lot more detail about how these work. So I'm not going to do it here. In fact, what I'll just do is try and write this quickly and just see if we can scribble something down here, just to give you at least one example. And maybe I'll work in black instead of green. So let's have a look. Let's give an example. Carboxylic acid. I'm going to go CH3 and then bond to COOH, and let's just do a simple one and add that, react that to methanol. CH3OH. So what happens is the methanol bit jumps onto where this bridging oxygen was, yeah, or where this OH was, and you're going to get this. You're going to get CH3 C double bond O, and then you have a bridging oxygen. I call it a bridging oxygen, and then you have CH3. So here we had methanol and ethanoic acid. So this here was ethanoic acid. Ethanoic acid. It's not that easy to write so neatly on these pads. Ethanoic acid, and here we had methanol. And here what you're going to have is, this is the ethanoic acid bit, so we call this ethanoate. But we first put the name of the alcohol. So we're going to say, right, this is methyl ethanoate. I know that's pretty untidy, and that is 2 words, by the way, methyl ethanoate. So the alcohol bit of the name comes first, and you put YL on to show that that's the alcohol bit, and then the carboxylic acid bit comes next. And you'll notice the molecules don't quite add up because we've also made water. Okay, water's come off. Now the conditions you need here is concentrated sulfuric acid, and you need a little bit of heat, not a lot of heat, a little bit of warmth, just warm it. We like to do these as pracs, so when we get back to school it'll be nice to do them. But that's just a very simple example on the last reaction of alcohol. But as I said, there's a lot more detail on this one when I do carboxylic acids. So if this hasn't helped you much, just go on to that. So next we look at aldehydes and ketones. I'm going to jump back just very quickly and go and look at the notes. We'll keep the annotations there. Let's go and have a look at the notes and see what they say about the reaction of alcohols. Yep, halogenation. Okay, we've spoken about that. Substitution, because the halogen went on and the OH group came off. Proceeds readily for tertiary alcohols. Like I said, that happens at room temperature, but slow and needs heating for primary and secondary. And then you can see it's laid out quite nicely. For primary and secondary alcohols, you need to treat the alcohol with concentrated H2SO4 and solid NaBr, and then that's going to produce the HBr in the reaction. And when it produces the HBr will react with the alcohol, and then you're going to get your haloalkane made and your water coming off. Alright, the sodium hydrogen sulfate is just a byproduct really. It doesn't do anything to the reaction. With the tertiary alcohol, like I said, you can just react it straight with the HBr. You don't need the high temperature, you don't need the concentrated sulfuric acid, and you don't need the heating. Right, it'll just do it at room temperature, and then again you get your tertiary haloalkane formed. So that was the first one. The second one we said was dehydration, and it's all here, elimination reaction, because remember you're just removing water. Water is eliminated, and the reaction is acid catalyzed. Excess of concentrated H2SO4 and H3PO4. Now I don't think I put that in the PowerPoint, I better go and look at it. Sulfuric acid is a very well-known dehydrating agent. It's very good at taking water off things, and so it'll work with the alcohol and pull off water, and you'll be left with the alkene. And then here it talks about the if more than one elimination product is possible, and that's when we say it's asymmetric around the alcohol. Like I showed you, you can get a major product depending on where the hydrogens are removed from, and they're always removed from the carbon with the least number of hydrogens. So it says it here, least number of hydrogens. So what would happen here? 2-butanol would react. That's the one I did in the PowerPoint. Let me just jump back here and see if I didn't. Oh, I did. I said here. No, that's the esterification. It was this one where I said, oh yes, here we are. Here's your catalyst that you need. You need sulfuric acid catalyst or H3PO4. Those are your catalysts that you need when you're dehydrating the alcohols. If it's a gas, then you need to heat it over aluminium oxide as well. Alright, so that's the reactions of the alcohols. I think we've done all of them, and then we'll move from that on to our next set, which is the haloalkanes. Okay, hope that works for you guys.